Hey, Chemsters, I am so sorry, but the last one ended up really abruptly. I had pressed some kind of a button on here and I couldn't figure how to undo it, and I just figured instead of losing all 22 minutes, I better just quit and pick up where I left off. So anyway, I don't remember what actually got recorded, so I may repeat myself, and if I do, I apologize. So let's try this again. Why is the lattice energy of magnesium fluoride about twice the amount of fluorine? Well, what's going on here? Let's see here. Here we go. Magnesium is a charge of a 2 plus, while lithium is a charge of a +1. All right. The charge is much more to do with the difference in this case, the radius. The radius has some effect, all right, but the charge has a lot more than the effect. Why do you think that is? Because these are whole numbers. All right, these are whole number values. The change in the radius is only a fraction of a nanometer. So these whole number changes are going to affect this a whole lot more than the fact that magnesium is a little bit bigger than lithium, all right? But what about the next one? Why is it almost 3 times the size of sodium chloride? All right, well, again, we're talking about the fact that magnesium has a charge of a 2 plus, while sodium has a +1. So that is part of it. All right, but what's the other part of it now? The fact that not only do we have a bigger ion here, all right, fluorine is smaller than chloride, all right? So before I was talking about fluorine and fluorine, so that didn't make a lot of difference. But here I have fluorine and chlorine. Fluorine is smaller, so not only do you have a larger numerator and a smaller denominator, between the two of them, you're going to make even a greater lattice energy. All right, so we could do this whole math if you wanted to, but just take my word for it. So both things are playing in here because you have both a different charge and a smaller ionic radius. Okay, now I think I've already mentioned that earlier, but there's something else I want you to consider. All right, so what about if I were to ask you lithium fluoride versus sodium chloride? What do you notice? That the charges are the same, +1, +1, -1, -1. So the same charge. So the only difference is look at the radius. Sodium is bigger than lithium and chlorine is bigger than fluorine. So the radius is greater, so the energy is smaller. That's why lithium fluoride has a greater lattice energy than sodium chloride. But how about, I'll throw this one out. What about lithium chloride and sodium fluoride? All right, again, same charges, but look what's happening here. Lithium is smaller than sodium, but chlorine is bigger than fluorine. You really cannot predict, and you'll never be asked that, okay? So be rest assured about that, okay? Let's go on to the next page. All right, so let's take a look at these. Notice we kept the chlorine identical, but what about the ions, the anions? All right, we have lithium and sodium and potassium and cesium, okay? So what can you say here? We do have a greater R value, and so what's happening is you get to be a bigger R value, your lattice energy goes down, all right? So as you go down the group, what happens ionic radius? All right, it gets smaller. So using Coulomb's law, why does the lattice energy decreases? Well, we've already said this before. Oops, that's a mistake, isn't it? Make that a positive. I don't know why I put a negative in there. Energy is inversely proportional to the radius. As radius increases, meaning going down the group, energy will increase, all right? No, I'm wrong about that. Take that back. Okay, I fix it now. So as radius increases, energy will decrease, right? So look what's happening here as I go down. Why is that? Because the protons of the nucleus are not as attracted to, the other electrons are further away, so it's easier to, split up, if you will, okay? In summary, the ionic radii increase as you go down a column. The ions cannot get as close to each other and do not release as much energy as the lattice forms, okay? So trends about the ionic charges. Look at this, sodium fluoride and calcium oxide. Again, look what happened. We have a +1, -1, and a +2, -2. That's almost a 4 difference, all right? So one says use Coulomb's law. So here's energy is equal to this, Q1, Q2 over R. So again, you have a +2, -2 versus a +1, -1. So the lattice energy is about 4 times the lattice energy of NAF. Not exact, but not too far off either, all right? So it says, in summary, the lattice energies become more exothermic or more negative while increasing the magnitude of ionic charge, and that's going to make a bigger difference than the radius. Again, the radius are only changing by a little bit of a picometer. Here you're changing the charges by whole numbers, okay? Let's go on. So problem number 6, it says arrange these ionic compounds in order of increasing magnitude of lattice energy. All right, so which one's going to be the highest lattice energy? You want the one with the greatest charge and the smallest radius. So that's going to be your biggest. So which one's going to be your smallest? It's the one with the lowest charge and the the largest radius. I hope I said that right earlier. So I'll say it again. The largest lattice energy is going to have the highest charges and the smallest radius. The smallest is going to have the smallest charge and the biggest radius. So look at these two first. Which one's going to be smaller, KBr or KCl? I picked those two because they have a +1, -1, +1, -1. So which one's smaller? Hopefully you got KBr because bromine's larger than potassium. And then over here, these are your +2, -2s. Which one is going to be biggest? All right. Well, between the +2, -2s, the one with the smallest radius. All right. So that's the order. Why don't you go ahead and do letter B and see if you can't figure this one out. All right. Hopefully you figured it out. I got, if I can click on it, here we go. I put it in that order because this is my +1, -1, +1, -1. This is my larger radii, this is my smallest radii, and this is my +2, -2. All right, they'll have the best effect. So in problem number 7, why don't you pause this and do A and B, see how you do. I mean it, pause this, think about it, write it out, and then come back, okay? Okay, hopefully you pause this and see how you did, all right? So which one will have the lattice energy higher? I said magnesium chloride because of the difference in the charges. The sizes are going to be about the same, so the +2 charge will make the lattice energy greater. And what about the other one? Well, they all have a +1, -1, so now it's all up to the size. Lithium fluoride has a smaller radius, so it's going to have a greater lattice energy. And then problem number 8, why don't you go ahead and do that right now too. Pause this and see how you do. All right, how'd you do? All right, so I went ahead and just found their charges. And so I found -3, -2, and -6. So hopefully you saw that this is going to be the negative or the smallest one. This is your middle one, and this is your biggest one, all right? So it says ionic bonding, what are some properties of ionic solids? I've already alluded to the boiling point, right? So here we go. The solids at room temperature, because it has such a high boiling point, it's going to be a solid for a very long time. High boiling point. It's brittle because of the plus and minuses along those planes. And it will conduct electricity when melted and dissolved. So while we're talking about melting, how does it melt? You have to have enough energy to overcome the attractions between the ions to separate them. So finally, number 9 is use ionic bonding model, determine which has the higher melting point. Which one do you think? Pause this and then I'll tell you what the answer is. All right, I got magnesium oxide because once again, it's a +2, -2 charge, which is higher than NaCl, +1, -1. So it's going to have the higher melting point. So that concludes 9.4. Sorry for the confusion, 22 minutes in the last one, but that is done with 9.4, and we only got one more video to go. So don't wait to be great. See you shortly. Bye-bye.